Dr. Jon Schoonover, Southern Illinois University.
For the saturated buffer, we're working up in Moultrie County, right at the north end of Lake Shelbyville, where the Kaskaskia and Okaw come together. We're right there at that kind of confluence of those two rivers, sitting there looking at a tile system, comparing a standard saturated buffer right next to a pitchfork design buffer. The reason we call it the pitchfork is it has three prongs that look just like a pitchfork. So where the standard buffer, you got a control structure, you come in and the water's diverted two different directions, 500 feet or so each direction, and then the water comes into the next chamber and gets saturated over that buffer. Our buffer with the pitchfork design has the same inlet, comes in, but it goes out into three pipes. So we're looking at about 500 feet of linear length on one, we're looking at 1,500. We're tripling that area that we're trying to treat with this saturated buffer. There's a couple things we incorporated into this design from our previous research. We saw when water tables would come up, we'd start getting backflow issues where water was actually coming back to our control structure. Those dispersion lines were behaving just like a tile would in the field and contributing more water. So we incorporated a backflow valve on the pitchfork design, so when the water went out, it couldn't come back. And so that's one of our main findings, is that we're seeing big reductions in water that are coming back. So instead of getting 35 or 40 gallons of water every time it storms, we're actually putting 15 gallons per acre per hour out into the field. So it's always going out. So if the water's always going out, then so are the nutrients. We're not having that nitrogen come back. So when that water gets up in a saturated area, that's what we're looking for in terms of denitrification. We want the microbes to break down the nitrate and give off nitrogen gas. So again, our main finding so far is we are seeing reductions in nitrate, dissolved reactive phosphorus in that pitchfork design, but the big take-home message again is that backflow valve not allowing water to come back into the stream. So we're putting out there, it stays out there. And then that third line, that dispersion line closest to the field edge, we also have a shutoff valve on that. So when the farmer needs to get in the field early in the spring, we can take that shutoff valve and close it and not put any more water into that zone. So that water just kind of dries off that area of the field. Then we still have two prongs that are still functioning in that saturated buffer. So another thing we're getting ready to kick off is some soil samples to actually bring them back to the lab and incubate them to see how much denitrification potential we have in those soils. So our soils, our site is probably a little low on the organic carbon end in terms of how much you need for a saturated buffer, but what our goal is to try to expand the areas that we can put these things. Because right now there's only a small part of the state where you have 1.2% organic matter and you have all those site characteristics that you need for these buffers. So our goal is to expand that area to other regions, and we're thinking this backflow valve will be helpful in that situation because the water tables, when they do get high, it doesn't experience that issue. That's one of our goals in the future, is to work with NRCS to get this design adopted as one of the programs that they can use. Not just tweak the standard saturated buffer, but maybe just add the flow valves to it, because I think that will expand the region they can be used in quite a bit. We've got a project up northwest of Springfield, Illinois, in the small town of Atterbury in Menard County. We're looking at water and sediment control basins. There's been a ton of research out there showing the impacts of these wascobs on sediment attenuation or trapping, but there's been very little research in terms of nutrient trapping efficiency or attenuation. So what we've done is taken a new site where they've got wascobs that were just recently installed, and we're looking at the outlets. We've got ISCO automated water samplers there that are collecting samples every time it rains. And then we've got some stacked pole samplers, which are basically a T-post with bottles on it. As the water rises in that wascob, it'll collect a sample. So we're sampling a series of two wascobs. So we have an upper wascob, a lower wascob, and then an outlet that we sample. And we're comparing that to another wascob system where we have that same setup, but we have a cover crop planted. And then we're also looking at two ephemeral gullies that don't have wascobs, that could potentially have wascobs on the future, but that's kind of our control, just to see what's going on in terms of nutrient attenuation. But the one surprising thing is looking at dissolved reactive phosphorus, it's about a 60% reduction almost. So it's quite a bit, so there must be some biological processing going on in those wasp cobs. The water's not in there for a long time. These wasp cobs hold it about 1.5 feet deep for about 12 hours and then they're draining off. So based on their design, they're getting rid of the water relatively quickly. We see about a 50% reduction in nitrogen in the wasp cobs compared to the non-wasp cob watershed. So we're seeing some pretty interesting things in terms of nutrient quality, and that's one of the things that is relatively new in the wasp cob arena because nobody's really looked at that nutrient attenuation capacity. That's one of the goals, is to see how effective they are at uptaking nutrients or reducing the nutrient inputs to streams. So if we find they are very effective, maybe that's something that we could compare to a grassed waterway where we're seeing a better result from this wasp cob system. So if that water pools there could be some denitrification, there could be some microbial assimilation going on. So yeah, it's a potential to expand.